because I think you are the most singular antitrust academic that I can think of, and you've been the most biggest inspiration for me. So on behalf of my former self, thank you so very much for everything you've done. Now, we're going to hear about a topic that is incredibly relevant to pretty much our daily discussions here in the EU and in the US. You're going to talk about the fairy tales about industrial policy, and you will focus on the digital industrial policy here and there, which of course relates to all of the buzzwords that we hear about very often now: self-sovereignty, EU stack, and a couple others. So I can't wait. I have actually no idea what you're going to say, which makes it incredibly exciting. We'll do it as we always do. We'll give you half an hour for presentation, then I will be asking 1 or 2 questions to get the discussion started, and then we have about 20 minutes for all of your questions over here. Thank you so much for being here, and Bill, the floor is yours.
No, thank you, Thibault. I can't think without the greatest gratitude for the very positive influence I've had by working with you and with other academics here like Martin Peter, whom I've known for quite a while. I think when you're fairly junior in the field, you have a deep appreciation for people who help you when they don't have to. People who don't have to spend their time and interest. And those are the ones I think you hold most dear as life goes on. And many of them are here in Amsterdam. So I'm delighted to be right here to talk about industrial policy and its implication for the digital world. And I'm going to go about this by looking at another episode of industrial policy on a big scale that dealt with the very biggest tech at the time, and look at some of its implications for the digital world. And then earlier experience is this one. Before there was the digital age, there was the atomic age. And for those in my chronological cohort, the great obsession and concern with tech at the time of my childhood and afterwards was nuclear power and nuclear weapons. That was big tech. That's why it was the atomic age. And discussions about the atomic age dominated policy discussions. And as I'll say, one of the key elements of that experience was the development of programs to promote the civilian use of nuclear power, the peaceful uses of nuclear power for a variety of different reasons. And this was a new technology that had enormous perceived benefits for society, but also potential risks. And the United States and other countries adopted a very elaborate set of industrial policy tools to promote its deployment and the development of nuclear power, especially to generate electricity. That experience, I think, has a lot to say about industrial policy initiatives involving the newest and most important forms of tech. I'm going to talk a bit first about the post-war vision for civilian nuclear power and how that came about, to talk about some of the implementation complications that arose, especially with the development of strong public policy efforts to promote deployment and to promote it quickly, to accelerate the use of this technology, and then to talk a bit about the significance for digital industrial policy. As you know, increasingly, there's a deep connection between energy policy and the digital world. To come into Washington, D.C., the flight path takes you over miles and miles of server farms now. What used to be simply countryside, horse farms, forests, are now server farms, and they're growing like crazy. And the big challenge to anything dealing with a green agenda and climate change is that to make the server farms work, you need electricity. You need a lot of it. It's got to be reliable. It's got to be relatively inexpensive over time. It's putting enormous pressure on the whole energy infrastructure, and what you see sprouting up all around the area in which we live are new high voltage electric transmission lines to bring power from the generation stations into this place in Northern Virginia, which is nothing but a collection of server farms. I've got my email address here, and I'm delighted to share the slides and continue the conversation. So to go back to the development of the civilian nuclear power program, in the United States after the Trinity test. This is the beginning of the atomic age. It's December 1942. A number of you have been to the University of Chicago and walked around the campus. Right now, there's a Henry Moore sculpture that is the site and the location for where the first controlled self-sustaining fission reaction took place. It was under the stands of an old athletic field, only marked by this sculpture and a plaque now. Interesting that they did the test in the middle of a large metropolitan area. That probably wouldn't be done now. But this was the site of it not all that long ago. And this was the grim conclusion of that first experience. That's Trinity just about 80 years ago. That is a shocking event for the scientists who worked on the project. When I was an undergraduate, I had a chance to interview a number of people who were involved in the Manhattan Project, including people like Eugene Wigner, the Nobel laureate, who helps persuade Franklin Roosevelt, persuade Albert Einstein to write a letter to Franklin Roosevelt saying developments in Germany make it urgently important that the United States develop a parallel program. Many physicists, engineers sought, in a sense, to redeem the sense of moral stigma that came from the development of nuclear weapons. There had to be a civilian use, and electric power generation was the great hope. The slogan at the time would be that you'd be able to generate electricity too cheap to meter, because this new technology would permit the generation of huge amounts of electricity at low cost. Medical treatments, radiation therapy being another application, and possible transportation uses. Nuclear-powered airplanes never quite caught on because they had to fly over densely populated civilian centers, but this was the vision for what would happen. This is a part of an interview I did with Wigner in 1974. Most men who worked on the Manhattan Project endorsed the goals of the program, yet none of us wanted to leave only a legacy of horror. To give some legitimacy to our work during the war, it was important to reap some fruits from the power reactor program. It's clear in talking to the scientific community that was involved in the program at the time that this effort, in a sense, to redeem the experience of the Manhattan Project was a crucial motivation for propelling the development of civilian nuclear power with a variety of public policy tools. This was the enabling environment that made it possible, and these are some of the industrial policies that brought this about. One was the dedication of a large network of national laboratories to do basic research related both to the theory of fission, but also to its application over time. These are places like Caltech, Fermi in Illinois, Argonne, a whole host of different laboratories dedicated to basic research. I suppose the theme going ahead is that one thing you can do with your industrial policy outlays is to support basic research. And I think most observers would say that's a healthy application of public funds to do basic research that might not otherwise be funded about the theory of the technology in question. Massive development subsidies given to industry to develop new reactor designs. The LMFBR is the Liquid Metal Fast Breeder Reactor Program, which was developed in the early 1950s as one energy source along with pressurized water reactors. The government hired and retained very skillful technical teams to work in the public agencies that were involved in the process. Scientists who matched the scientists in the academic world, and certainly in the private sector. You had in the nuclear energy complex within the government an exceedingly high quality of personnel to oversee and manage projects. So instead of hollowing out the civil service in some sense, this was an effort to build a civil servant cadre that was able to do analytical work and oversight at the highest level. Major spillovers that could be called industrial policy contributions that came from defense applications, especially the construction of reactors used for nuclear submarines. The Navy's nuclear submarine program became in many ways the training site for personnel who would ultimately migrate into the private sector to operate nuclear power plants. The head of this program was a Navy officer named Hyman Rickover, who established in his program the highest standards of quality control and engineering, an extraordinarily rigorous program. One of his accountability systems was that if you worked on his submarines as a contractor, there was a requirement that you personally went on all of the first test dives of the submarine. So you were told in advance, you're going on the first trips. And if it doesn't work, you'll know about it before anybody else. And I'm told by those who went through that experience that there's nothing quite like the sight of water squirting in through bad welds at high pressure that makes you think, if I ever get out of this alive, we're going to work on it better the next time. So he had a variety of approaches to instill accountability among his engineers, but the consequence is that you had highly trained personnel coming out of the government to go into the civilian power plants, and they were indispensable to making them work, to anticipate a theme. There weren't enough of them coming out to make the large number of civilian plants work effectively. So instead of having very high quality personnel spread throughout the sector for deployment, you had a mix, and it is the uneven quality of personnel that led to serious breakdowns that retarded the program. This is one of the biggest industrial policy measures that has a big tech connection, a severe limit on tort liability. The civilian power sector said, we're not going to do this unless you put a cap on our liability for any serious adverse effects. The worst being a breach of a containment vessel, a massive spread of radiation, and hundreds of millions, if not billions of dollars of claims, even in 1950s, 1960s dollars. The civilian power sector said, if you don't cap the liability at a sensible level, and their idea of a sensible level was a very modest level, we won't do it. And the US Congress adopted a law that capped the liability at a few $100 million per event, where the maximum exposure could have been multiples of that amount. So this is a significant industrial policy gesture to induce the industry to build and operate these plants by limiting their tort liability. As you've seen in a number of countries, on tech, on digital, this is a big issue about the responsibility of the owner of a platform for content. Where platform owners often say, we are not editors, we're just the conduit. We're not publishers, we're not exercising editorial judgments. You can't hold us accountable for providing the channel through which the information flows. And that's a major part of the deployment of the related relevant systems in the US. Is an important limit on tort liability. Well, this was crucial to the deployment of the technology. And the last item, which was a crucial externality to be addressed, is where do you put the spent fuel rods after you've used them up? Where do you store them? Ideally, you'd have a permanent waste disposal solution. And the best of the solutions was to go to places like Nevada, the so-called Yucca Mountains, which desolate, no human beings, probably not many animals, just way out of nowhere, and you dig into the mountains and you put it there. The state of Nevada was not fond of that. It said, we don't want it. And surprise, surprise, none of the US member states wanted that repository. And there weren't foreign governments that were willing to take it. So this crucial part of the entire fuel cycle is never ultimately addressed. I guess to anticipate an issue that comes up more and more in the future, if you're thinking about a subsidy program, if you're thinking about a set of subsidies, have you thought about the entire life cycle of the technology and what has to be done with the consequences of the application of that technology over time? Here the answer was, we'll get to that later. Well, it's 70 years later, we haven't gotten to it yet. The waste materials are being stored in what are called temporary storage pools associated with each generation facility instead of being located and treated at a central location. The consequence of the industrial policy mix: subsidies, limits on liability, government-sponsored R&D programs to improve the state of the art, government defense programs that had as a spin-off tremendous improvements in reactor design and the training of personnel. In many respects, again, the government was the training locale for people who became operators for fission plants. And the result is that, whoosh, the deployment of the technology takes place at a strikingly fast pace, with literally dozens of civilian generation plants scheduled, launched in the 1950s, and through the 60s as well, several hundred planned to be deployed around the country. There's a green backlash to this. Not on carbon grounds. Carbon hadn't received that much attention on emission grounds. A well-functioning nuclear power plant is pretty green. And well-contained and shielded. The exposure you get from standing at the edge of the plant's circumference is decidedly less than you get flying from Amsterdam rural, at 30,000 feet. So it's less. You're at greater risk in exposure there. So, but the concern was that you're going to have a catastrophic event. And in a way, isn't this part of the concern with AI? The AI in some ways resembles the famous scene in Fantasia, The Sorcerer's Apprentice, where you have a remarkable power given to a single human being and things sort of get out of control. That humans lose the ability to effectively manage. Here the concern was you're rolling this stuff out so fast and you're going to have disastrous mushroom cloud-like experiences. And the solution in the US that has long-term implications was the legal opponents and advisors to the rollout decided to work with existing laws that gave the government a deeper role in evaluating the likely environmental impact of specific decisions under what was called the National Environmental Protection Act. And the plan was to bring challenges that force the preparation of detailed environmental impact statements. And the conscious plan was, by stretching out the construction of the plant, you would make it vulnerable to inflationary pressures that in many instances double the price of building the plant. There'd be lots of cancellations. That technique has resulted in the creation of a number of procedural hurdles today to building things like long-distance transmission lines. If you want to use the kinds of turbines that you see in the journey from Brussels to Amsterdam, the many turbines that are there, in the US, those wind fields are located well away from the major metropolitan areas. Lots of places for turbines in places like Nebraska, North Dakota, but that's far away from Chicago, Denver, Los Angeles. So you have to bring the juice using high-power transmission lines. What obstacle exists? All of the procedural hurdles, a cascade of barriers that make it difficult to get approvals right down to the county or municipal level to string a long-distance transmission line. So the strategy that was very successful for the green community in slowing down this deployment in some ways stands directly in the path of making broad use of renewals. And there's an effort now to try to peel those back, but they're pretty well embedded in the system. In part because this system was rolled out, I'll argue, too fast by reason of the subsidies. You had mistakes. 3 Mile Island is the best known. There was another outside the Detroit metropolitan area called Fermi 1. 3 Mile Island, in a sense, showed that the basic engineering of the systems was quite rugged. The operators, somewhat ineptly, did everything you could to provoke a serious nuclear event, to have a core meltdown and then a breach of the containment vessel. If they'd had a notebook saying, this is what you do to promote an event, these are the steps you take, they followed the notebook, but the system still held up. So the engineering was pretty tough. The operators were not so good. And you saw in a number of studies the more serious incidents, but the lesser incidents, you had a horrible mismatch between the scope of the deployment of the technology and the capacity of the operators to run these facilities well. I guess footnote for tech for the future, if you're rolling out powerful systems, do you have the people to take care of them well, and as I'll say, to anticipate what could go wrong in the actual implementation of the systems themselves? The interesting counterfactual in the US is what would have happened if you hadn't had the big push to roll out this new energy generation source. No liability caps, no liability limits, no big subsidies for the construction of facilities. If it had been a more gradual process, my intuition is that you would have had a couple of things. One is because of the absence of tort liability waivers, you would have had more rigorous testing of the technology at the front end before you went live with it. That you would have spent more time, you would have felt a need in order to get financing and approvals, you would have spent more time testing the technology. There would have been more prototyping at the front end. You wouldn't have had the construction of plants as quickly, certainly not. But what you might have had is the elaboration and introduction of the technology in a way that avoided the incidents. That was rolled out at a point at which you had the human capital to run the facilities well. The technology was still more robust and rugged, so the possibility of an adverse event was minimized. And as a consequence, you have a fuel cycle that becomes sustainable. It was not in the US. No new nuclear plant construction since the mid-1970s, 50 years ago. No new facilities completed. Talk now about building smaller modular units, but in a way, the consequence of what I'll call the aggressive industrial policy strategy, saying the top priority is to get these systems online and to deploy them broadly, is that ultimately poisoned the operation of the fuel cycle, which is only now coming back into the field of vision because in so many ways, though it does have hazards, it's a lot more green than other generation techniques. Here's a fascinating foreign policy spillover as well. Part of the sense that there had to be broad, peaceful uses of nuclear power and that the US would do something to make that possible was that this should be made available broadly across the world of allied nations and at least the non-affiliated world. And the promise of the US was delivered through a program called Atoms for Peace, where the US said, we will build you a research reactor. We'll help train your people to use it so you can do basic research. Now, there were some safeguards put in place so that enriched uranium and plutonium residue from the operation of a research reactor couldn't be diverted for bomb programs. But those safeguards were modest and they weren't really very intrusive and they involved very much self-certification. That is, you're using the facility for research, aren't you? Yes, we are. Peaceful research, yes, for research. We are using it. Here's some of the beneficiaries of the program in the 50s, 60s. India, Israel, Pakistan, South Africa, what do they all have in common? Build-ups. Now, would they have gotten there on their own without this program? Entirely possible. High levels of technological development, high capacity. Was this program almost certainly a boost in getting over a big hurdle to put this in place? Yes. A consequence of the push to get the technology out there and adopted broadly, not just in the US, but globally, is that nobody thought through quite carefully enough the possibility of what becomes known in the literature as latent proliferation. Yeah, Martin Peter.
What was the benefit for U.S.? This foreign policy?
It was seeing two things. One is that it shows our commitment to make sure that this technology will be used for good. And that the benefits of doing that ultimately, I suppose one thought, in the form of additions to the electric power grid would be made universally available. The other was to achieve a foreign policy gain by showing openness. The Truman administration had said, we're not telling anybody anything about this process. Eisenhower said, for these purposes and applications, we're making the technology widely available and known. And I suppose it was a way to wed the U.S. interests to those of countries that wanted to be able to say, as a matter of prestige or science, yeah, we have a research program, and we have a functioning research reactor.
It seems pretty bleak benefits compared to the dangers involved.
Ex post, it sure looks that way. And I would say ex ante, one might have thought that there'd be a lot more concern devoted to that. That is, to think through what happens, if you're not watching where it's going the whole time, with intense regular inspections and a cascade of procedures that you use to make sure that the fissile material isn't being diverted, that's the start of your uranium enrichment program, right there. for both, well, I should say your plutonium production program right there. And that's how you start. That's how you start making a bomb right there. I guess a lesson for tech and other technologies, tech features, digital features that have great promise benefits, but hazards, is that part of what you'd like to see as part of the deployment is an effort by observers, insiders, to say what might go wrong. Not necessarily to conjure up horror stories, but to sit back and say what might not work as we expect. What could be the paths in which the deployment would take place? I had a long conversation once with Vinton Cerf, who probably did invent the internet. I mean, there are thousands of people who claim credit for it. He could rightly claim credit for it. As you asked Vinton Cerf, what were you doing at the Advanced Research Projects Agency in the 1960s, developing this so-called internet capability? What did you want to do? We wanted a low-cost, reliable communications framework that would enable people with relative ease and cheaply to talk to each other and to build communities. That's what we wanted to do. He said, nobody was thinking how this could go badly. Nobody was thinking how these networks could be used for malicious purposes, both in the world of social media, or that you would have what we simply call wrongdoers using it to rob money, to penetrate databases for malicious use. Said nobody was thinking about that in the office. We had no project going on. Everyone was so convinced that this is unmistakably a great thing that the question of implementation proceeded without concerns about what could go wrong. And I suppose I understand that. I mean, suppose you're on the threshold of a great advance in some area. It's a bit of a downer to immediately start thinking, wait a minute, what could go wrong? And there's no new technology for which something wouldn't go wrong. In my days with the law firm, spending lots of time working for the company then known as McDonnell Douglas, one of the McDonnell Douglas engineers once told me the safest airplane in the world is one that never leaves the ground. That's a really safe airplane. That one is not going to crash. That's a really safe plane. Said the only way to know if you have a good airplane is to fly it and to test it. So if you count up all of the adverse possibilities, that's probably a formula for paralysis.
Yeah, but this case started with a bomb. So here they should have known that it's very, very dangerous because it started with a bomb.
I think there was also, with this, if I had to throw another consideration on the table, there was a dramatic underestimation of the cleverness of people living outside the United States.
Yeah, okay.
It was well known that, yes, the United Kingdom was going to have one of these, that the Soviet Union did have one now, that it wouldn't be long before France was in line to do the same, and soon after that, China as well. It was certain that that was going to happen. But the thought that everybody else was going to get on board to be able to figure this out and cleverly discover ways to evade the safeguards, especially with a trusting overseer on the other side, that was dramatically underestimated. Yes?
What's the role of the Cold War or geostrategic considerations in this? Because I can imagine that if the US doesn't provide India with a research reactor, then maybe the Soviet Union did.
I think I'm certain that the view in part was that if we get there first, we can control it, and if we don't, in the race for hearts and minds, and maybe economies, the Soviets will be there first, and you want to let them get the jump on you. And the other thing that's happening at this time in the race for scientific preeminence, this is the mid to late 50s when this really launches. You don't have to have lived through it to know the other source of anxiety within the US, that the world as a whole would perceive the Soviet Union as being far ahead in the race for preeminence in science, and that development was what? Pardon? Space program. It's Sputnik. It's, oh my God, they're there first. And that was an enormous public relations and political coup for the Soviet Union. To be first with satellite, and then with Yuri Gagarin being the first person to orbit the Earth. So this was a way to show the world our science is truly state of the art, and we're as good as anyone else's. Yeah, I finished. Right. Okay. Let's see. 5 more hours. Thank you.
5 days.
5 days. 5 days. Good.
We have food. We provide with beds. No worries.
The doors will be locked on the outside.
Cast in quietly. All right. Let me.
The other I'll just mention on the next generation, or the next possibility, is fusion. And there are massive subsidy programs to achieve the construction of fusion-based generation facilities as well. When I was, an undergraduate interviewing people about this program, the head of the Princeton Physics Laboratory, a distinguished physicist, said in 1973, the reactor could provide a virtually unlimited source of fuel for the future. And one thing you often get in industrial policy programs historically, is extravagant promises of effectiveness ex ante. If I'm going to justify the program, I don't talk about modest improvements. I talk about changing the universe forever in a big way. That's why you should give me big money. And Gottlieb was a recipient of the funds. We expect to see the remaining scientific problems solved by the end of the decade. He was speaking about the 1970s, just to be clear about that. This is the experiment in 2022 that did what the University of Chicago experiment did in 1942. So they have just gotten to the point in 2022 that they've demonstrated the feasibility of the concept. It's a long way from this to a power generation station that works 24 hours a day and generates electricity. Mel Gottlieb was not only 50 years off, but probably 60 or 70 years off as well. Depended, I guess, on what decade you were talking about. Again, something we see historically with major industrial policy, high-tech development programs, is the promises are heroic in the extreme and have to be discounted, I think, in a realistic assessment. I don't know what the discount rate should be, but it's significant. Okay, couple of lessons to wrap up. What does this mean for new technology, including digital in particular? In practice, the journey from the proof of a concept to its effective full-scale deployment ideally would take some time. Prototyping, then the full rollout of the system. It's in the prototyping that you get a sense of what's working and what isn't. You've got to build a commercial supply infrastructure that will support it. So if you're going to spend money to promote the development of the system, you want to think about the entire life cycle, not just a specific part of it. It's not going to work and work effectively unless you have good talent to do operations and management. The people who are running the systems have to be up to the task. And I guess a hazard for any company that's rolling it out fast, especially if you're a tech company and you feel an imperative to get it out right now, because if you hesitate, somebody else is going to sweep past you and you'll be in a distant second place, is that I think there's a disposition to move quickly, to put it out there and retrofit as necessary later on. But if you wait, you achieve a hopelessly distant second place position or worse. So that you want to push things out quickly. It means you might not be working quite as hard to get just the right people in place to do the work. And the danger for new technology is if you're not careful, you have a 3 Mile Island experience. You have an Exxon Valdez experience in the Gulf of Alaska. That was a major oil spill. You have the blowout of the production platform in the what's called the Gulf of Mexico. You have events where the technology is in some sense endangered or set back badly because you have a visible adverse event. I'm not sure just what that event might be in some of the tech areas, but there are a number of commentators thinking about those. I don't think they're inevitable, but if you look at these earlier experiences, you can see the vulnerabilities of the new systems that would tell you a lot about where you have to be spending your own time and effort to make sure that it works. And I think part of the exercise you have to go through is truly to have your own team, maybe advised by others, where you sit down in a somewhat grim but ultimately productive way to say, what could go wrong? Here are our expectations about how this will be used and deployed, but how could it go bad? What could go wrong? Can the systems be hijacked? Will the systems define effective control if they're rolled out too quickly? Last slide. I know that some of these earlier experiences are, in a sense, unrepresentative. I do think they're informative, though, especially to look at some of these experiences. And the atomic age was a much bigger deal than the digital age. It was the atomic age, too, because the sense of imminent disaster was so close. And the fear that one might not live out of one's childhood because it would go out of control. That surprises and unintended consequences emerge when the subsidies dramatically accelerate development. And you don't have the more deliberate process of testing and assessment that takes place. Exaggeration of expectations, great underestimation of costs, and a competition policy concern. You want to diversify where the money's going so that you can get people with new ideas to try them out. And if you're not building the technical capabilities and applying them to deploy the technology, then you're falling way behind. And I'm just going to finish by echoing a comment that Paul Seabright, I think, made in a conversation with Thibault in the podcast. Paul's observation about how we just don't have the honesty in public policy to lay out what things are really going to cost if you're going to do it, and to lay out hazards. My favorite point on the other side of that is the experience with the Marshall Plan, which didn't deal with high tech. But George Marshall, the Secretary of State, the namesake of the program, goes to Congress in 1948 to ask for the money. And in a way that's quite refreshing, and you can see his testimony. He's not a great orator, he's a clumsy speaker. But the substance of what he has to say to the Congress is bracing in the modern public policy environment. He says, it's going to be really expensive, and he gives them a number, and they pick themselves up off the floor. He says, that's just the beginning. It's going to cost a lot, as opposed to it's going to be free. Second, it's going to take a long time to work. We're going to have to be at this for decades. Not an American strength when it comes to policy initiatives often. If it works in 6 weeks, that's fine. Long-term, 6 months, but then we're done. Third, he tells them, he looks at the committee right in the eye and says, I can't tell you it's going to work. I don't know. He said, I can tell you that we will regret it forever if we don't try. The stakes are so high, we have to do it. It's been a long time since I've heard a public official in the U.S. try to pitch a program with this approach. I have to say, expensive, long-term payout, success uncertain, but we must do it. We have an obligation to do that. Good luck, talk that way now. You talk that way about your program instead. Glad to discuss this. Thank you again for the chance to be here.
Thank you very much.
Just to be clear, the possibility of nuclear conflict is so remote that it's only a hypothetical possibility. Yeah, it's way in the past, long gone.
I'll ask you one question, burning, very hot question that I have, very controversial, and then I open the floor. Would you rather have competition agencies and data protection agencies and IP offices to kind of look at the balance we may have between those, as you were putting out on the previous slides, age-rated expectations versus the risk of not doing anything in the field? Or would you rather have those agencies do what they do, which is competition agency go for competition, and then somewhere in the police for office have the trade-off made between competition and those?
At a minimum, I would like them to be part of the conversation in that other forum in which decisions are ultimately taken. I think agencies, when they scan their whole experience studying industries and looking how industries evolve, I think they learn a lot about the effect of subsidy programs and industrial policy programs. They might not reach ultimate judgments about the utility of this technology or another technology, but I think they're in a very good position to say that a number of things I've flagged here as being consequences, intended or otherwise, that these are going to happen if you do things this way, and this is what you ought to think about. So, perhaps it's a forum where you bring together the scientists who are going to advise about the way in which money gets spent, the office that will be responsible for handing out the money and the subsidies over time or designing the other mechanisms. But I think having, just to take the competition agency, that it's got a lot to say if it brings its knowledge to bear on these issues, and to have, by way, certainly with tech, by way of thinking about side effects, I'd like the Data Protection Authority in there to say, this is what we've learned from our experience about where vulnerabilities creep up and how you account for them in advance. And yes, to have the promoters of the approach there in the row too, and saying, here's what happens if we do nothing. Here's what happens if you have no program at all. And my own bias would be my suggestion about thinking through these other things is not a formula for timidity or inaction, but to make sure that you understand, eyes open, what's coming at you and what you're going to face, so that you develop approaches for dealing with potential hazards. So it's not urging stasis, but urging a reflection on potential obstacles. And I would count on the advocates for the program to be in that room too, to say, if you want absolute safety and certainty of one sort, then you do nothing, but here are the bad things that happen because you did nothing.
And that forum, would it be something like the DRCF in the UK, where you have all the agencies gathering once a month? Or is it something like we may already have in the EU or in the US? Because I can't find, from an institutional perspective, anything that kind of resembles that.
I don't think we have it yet. No, I don't think it exists yet. Where it exists, it exists probably in the form of ad hoc relationships that are focused on specific projects. But I don't have the sense of a systematic process. For example, I mean, I think, depending how you count it, the total amount of infrastructure, chips, and other investments that the Congress approved over the last 4 years is about $2 trillion. Everybody has $1 billion, that doesn't matter, but $1 trillion is a lot of money. And that's one shot to spend this on a variety of different purposes. I have no idea of how, there's an office in the Commerce Department that has some of it out. The Department of Transportation does some, energy, but I have no idea of a sort of a common methodology that they might use to decide who gets what money. And the concern that outside observers have is that it all goes to legacy companies. Intel, in the case of chips, which is a big recipient, which is a good candidate for a takeover now because they're having such a tough time. So how are you handing out the money? What criteria are you using? Who's involved in that process? Pretty opaque.
All right, time for the Q&A. This is not recorded, so feel free to share some controversial views.